So far we have looked at circuit elements which are present in this arrangement, and basically we have looked at voltage divider circuit as well as an RC circuit. For example, this is the circuit looked at, and that is an abstraction of this circuit that you will encounter in your electrophysiology recordings. And previously what we did was to charge a very large capacitor like this one, the 2200 microfarad capacitor, and then saw how the charging takes place. But quite often we will not be measuring it using a stopwatch, but we'll be using an oscilloscope to look at the waveforms. And because the signals that we encounter are of much higher frequencies, and the capacitors and resistors are such a way that the time constants we encounter are of much smaller values. So in order to do that, we will use an oscilloscope and a signal generator. Here we have an oscilloscope which also has a signal generator, as I had mentioned before. I have taken the output of the signal generator and provided it to this point. This R, which is the 10K resistor, I have connected to this capacitor in this line. And this point should then be the ground, which corresponds to this point. This junction is this point. And of course the input is into this point, which is here, right? So this is A, that is here, and this is B, and that is here, right? So we have to connect the ground to this point, right? And this oscilloscope being the same one which also generates signal, the ground is common both for signal and the scope. So that's why we need only one probe. And we have to look at whether the signal, what is signal that is going in. So here is the signal that is going in, and you can see it is a square waveform, right? Square waveform. To see the more periods, we can change the time base, right? So you can see that the number of cycles are now visible, and if you go to this time scale, you can measure the period, which is this is 0.1 milliseconds per division. So 1, 2, 3, 4, 5 divisions. So that is 0.5 milliseconds, approximately 2 kilohertz, right? So that is observed here, 2 kilohertz waveform. Okay? So the oscilloscope is currently measuring output of the signal generator, which is 2 kilohertz. Now let us switch back to the other scale because it is more visible. Okay, and I'll change the. Okay. Now in this scale, we are currently measuring the input, and if you change the measurement to that across the capacitor, right, and which is the across at this point, which is intracellular measurement lag, right? There's a cell without any leak or any other conductances, just capacitance, and this is the shape. So unlike in the previous case where you use stopwatch, we can measure this time reading off from the scales here. So let us make the scale better for us to read out. Okay, so that's a reasonable scale to read out. So roughly 3 volt is the range of this square waveform max. So 1, 2, 3, 4, 5, 6, 3. It's going towards 3 volts. Now the 3 volts, 95% of that is 0.95 into 3 is 2.85. The time is 4 into 50 microseconds division, so 200 microseconds, and R is 10 kilo ohm, and the C is 4.2 nanofarad, So tau, 3 tau equal to 3 RC, approximately equal to 3 into 10 into 10 at 3 into 4.2 to 10 at minus 9 nanofarad, around 126, roughly 126 microseconds. This is the ballpark of, as I said, there are stray capacitance and so on, and the output impedance of this and so on matters. So approximately the time scale that you see is correct. So that is how the RC circuit behaves, right? So it's clear, very similar to what we saw with the large capacitance and the LED. Now we want to see if I increase, say double the capacitance. So I have another similar capacitance which I will connect in parallel to make the capacitance double. So here I have connected capacitance double. Now you can see the time constant has increased, right? So it takes to saturate near this one at roughly 2, because C is doubled when the capacitors are in parallel. So it should take double the time, right? So that's not surprising. So I'll remove this to get back to our original this one. Just to recap the theory, we are giving input to this RC circuit. So here is the square waveform that we looked at, and we had our probe here to look at how the capacitance is charging. So the theory is that this current through this is equal to VI, the input, minus VC, which is VI minus divided by the R1. This should be equal to the current through the capacitor. If the VC is the voltage across the capacitor, then the current through the capacitor is C1 dVC by dt, right? And if I integrate, if I take a dVC on one side and VI minus VC on the same side, and take all other things on the other side, and if you integrate left side and the right side from 0 to t, correspondingly they should go from 0 to VC, then you would get the solution which would lead to this, and which will turn out to be this, which is what you have learned in the theory, right? And what we are saying is this time constant, what we calculate theoretically, is what we get when we do the measurement using this oscilloscope. Now let us consider this situation where there could be some channels in on the membrane, and they are in, of course, introducing conductances in parallel with the capacitance, right? So it should mean that the circuit we are dealing with is sort of like this, right? So what will be the behavior of this RC circuit if you put a resistance across this? Of course, the first thing we already know is that eventually when the capacitor has charged, this voltage should reach VI into R2 by R1 plus R2 as a voltage divider, right? That is what would happen. But during the transient, what would happen? What would happen to the time constant, right? So we may think that, okay, this R will take out some current from the circuit, and so there will be less current available for the capacitance to charge, and so it may take longer to charge. But in reality, that's not. So you may actually expect the time constant to increase by the introduction of this R2. Let us see in theory what would happen. So now this I is the sum of these two currents, I1 and I2, and so I is equal to I1 plus I2, and if you write down I is equal to VI minus VC by R1, and so equal to sum is the sum of the currents through this, as I said, VC by R2 through this, C1 dVC by dt through this, right? So similarly, if you rearrange the equations, you can write and represent this thing as alpha by R1. Okay, so alpha is R1 plus R2 by R2, and if you can rearrange this thing to write down as 1 by R1 di minus alpha Vc. Left side is of course C1 dVc by dt. If I rearrange it and write down the integral form, then you will get dVc by Vc minus Vi by alpha equal to minus alpha by R1 C1. Integral left side ranging from 0 to Vc and right side ranging from 0 to t. Then you will get the solution to be of this form, right? And so what you can see is the time constant, which is here, is R1 C1 by alpha. What is alpha? R1 plus R2 by R2, which is always greater than, solution is this, R1 C1 by alpha, and alpha is greater than 1, which means tau is less than R1 C1. Our previous R1 C1 in this situation, the tau which is now there for this circuit by the introduction of this element, which is sort of analogous to the membrane conductance in parallel to that. By doing that, what we are doing is reducing the time constant. Okay, is it true? So we will plug in another 10K across this. So you should observe here. So that we can also do another thing, which is to actually store this oscilloscope, though it does not have two channels, it can actually store this waveform. So let us go and try and do that. Yeah, it is saving. Okay. Now this waveform is saved, which means I can now, in the next situation when we are having the new waveform being displayed, I can load the previous waveform because it is stored in 0, 3. Okay. Load data. Okay. So let us now, to see this, we should go into this. In this I should go to hide and show this waveform. Yeah. So that was our same waveform. Okay. So now you can see that this waveform saved. Of course, the reference point has shifted in this direction because I think the AC waveform is getting stored. But here you can see it is saved. These reference points are different, so I can shift it to match it if needed. So let us first go and now plug in this 10K. Okay, and see how this waveform changes. So you should watch the blue waveform. See that now it is, of course, the amplitude has reduced to half, but important thing is that it is reaching the saturation much earlier than this, right? And the ratio which we have is R1 equal to R2, which means this is 2, so tau is half that of R1 C1, and that you can see because the other one reached max here and this max reaches some max somewhere here. Let us align the Y position of the blue to match this position. Y offset. I'm going to align the Y offset to this. Okay, and then I will go and change the X offset. X offset. Y position. Okay, so now they are aligned, and you can see that they start off near same point. This reaches 98 points somewhere here, and this reaches somewhere here. So that's double the time. So this R, when you add a conductance in the membrane, actually the time constant decreases. So it is very clear that if you have a circuit like this, and if you want to actually make a voltage appear like this across the membrane, then the injected voltage corresponding to the current should be such a way that there is a voltage produced here which will produce this voltage at this point. And how is that possible, right? And that we do by what is known as capacitance compensation. Okay? This is the simplest form of capacitance compensation, where you introduce a capacitance in series with the circuit, such a way that the shape produced here is more or less, or at least better than the exponential curve that you would have got without it. So if it goes from here to something better than like this, then you would say that, of course, you have compensated for this capacitance. Now we also know that even if there is a leak here or a channel here, the shape is same, the effect will be still compensation of the capacitance. Now how would this circuit function, right? To look at that, maybe we can abstract it, the C to be here, because it's in series. It doesn't matter where you place this capacitance. So the net capacitance here is this in series with this. So each of them have the corresponding voltage across them, VC1 and VC2. Okay, and so the total VC is the sum of these voltages. So if there is a net capacitance here, which we know will be this because they are in series, then this circuit acts as a single RC circuit. And we already know the solution for such a circuit, right? Which is VC is VI and so on, right? And so VR corresponding to that will be VI e raised to minus T by RC. And what will be the current I? Then I will be VI by R1 e raised to minus T by RCT. CT being the total capacitance, right? And this CT you can see will be less than either C1 or C2 because it is this product divided by sum of C1 and C2. Now this equation, now if the I is this, then we can write down the integral for finding VC1, which is I integrating I across the C1 alone, right? To get the charge divided by C1 will give you the voltage across it. So VC1 is this. Of course, we can integrate that and we will get this form, right? And what is interesting here is that now the time constant is R1 CT, right? And what we know is that because CT is less than either C1 or C2, R1 CT will be less than R1 C1, which means we have improved upon time constant, meaning the waveform should rise faster. Now let us go and test that in this circuit. So we have this waveform already stored, right? And we would like to now go and change or introduce the capacitance in series with the circuit. So let us take an equal value capacitor as same as this one, right? And then wire it up. So now the input to the circuit should be through the capacitor. So we have wired up the capacitor like that, and we are giving the input to the capacitor. And you can see the waveform has now much faster time constant. So let us see whether we can load the external. Yeah. So now we have loaded the previous waveform, and now we can shift this down, right? In. Okay. Shift it down to align with that, and you can clearly see that we have improved the time constant. Is it not rising much faster compared to this? Naturally, it is rising to a smaller voltage as expected. Yeah, so this is the basic notion of capacitance compensation. Of course, in an actual amplifier, like for example, in this is the interface for one of the amplifiers, and you can see something called pipette capacitance neutralization, which works in the same principle but for neutralizing the capacitance from across the pipette glass, okay, from inside the pipette to the outside of it. That is where capacitance neutralization here works for neutralizing this capacitance across the electrode. This is an example of a circuit given in the textbook, Johnston and Wu, and you can see it's a more sophisticated capacitance compensation called introducing a negative capacitance. But you will see that this capacitance here in some sense work in the same way as this capacitance here. Okay, but of course it is amplified and so on. But so basic principle of capacitance compensation is demonstrated by this circuit, and the effect of that compensation can be seen here. So we have in short summed up basic RC circuit, which represents this circuit in the cell and the pipette. We have looked at how the time constant will change when you have some conductances in parallel with this capacitance, and that is done by analyzing the circuit. We saw that the time constant decreases, and when you have to compensate for the capacitance to make more rectangular waveform appear across the cell membrane, you need to do compensation, and this is a simple example for doing capacitance compensation, and we saw the effect of that compensation in this experiment.